Hello everyone, and welcome to GIS and Engineering Academy. I'm thrilled you've joined us today. We're about to have a discussion on soil salinity and how remote sensing technologies play a crucial role in mapping and managing this environmental challenge. Let's start our discussion with a fundamental understanding of what soil salinity is. Soil salinity refers to the accumulation of water-soluble salts within soil layers. These salts can significantly impact plant growth by limiting their ability to take up water, essentially creating a drought-like condition even in well-watered lands. The scope of this issue is vast. It is estimated that over 800 million hectares of land globally are affected by soil salinity. This represents a substantial challenge for agriculture, especially in arid and semi-arid regions, where irrigation practices can exacerbate salinity problems. Understanding soil salinity is crucial for sustainable agricultural practices and for maintaining soil health. Moving on, let's explore the main causes of soil salinity, which are categorized into natural and human-induced factors. Naturally, soil salinity can occur from the presence of geological salt deposits, which dissolve and accumulate in the soil over time. Additionally, in coastal areas, seawater intrusion, especially during storm surges, or in regions with overdrawn groundwater, can significantly increase soil salinity. On the human side, the causes are often linked to agricultural practices. Irrigation with saline water, which may be the only water source available in arid regions, is a common cause. Moreover, inadequate drainage can lead to the accumulation of salt in the soil as water evaporates, leaving salts behind. These human-induced factors are often preventable or manageable with appropriate agricultural and land use practices. As we understand the causes of soil salinity, it's equally important to recognize its effects, which span across agriculture, the environment, and the economy. In terms of agriculture, soil salinity drastically reduces crop yields. Certain crops are more sensitive to salt than others, which forces farmers to alter crop selection, often opting for less profitable options. From an environmental perspective, soil salinity leads to a significant loss of biodiversity. Saline soils can disrupt the natural balance, leading to the decline of native plant species and the organisms that depend on them. Additionally, the physical structure of the soil deteriorates, reducing its ability to hold and transmit water, which further impacts plant growth. Economically, the effects of soil salinity are felt heavily in the agricultural sector. The costs associated with managing saline soils are high, involving investments in better irrigation systems, soil amendments, and sometimes even land abandonment. These challenges result in considerable financial losses across the agricultural industry. Let's now shift our focus to a powerful tool in the study of soil salinity: remote sensing. Remote sensing is a technique for collecting information about objects or areas from a distance, typically from aircraft or satellites, without making physical contact. This technology is crucial for environmental monitoring, including the mapping of soil salinity. There are several types of sensors used in remote sensing. Optical sensors, which can capture data in visible, near-infrared, and shortwave infrared light, are particularly useful for detecting signs of salinity, such as salt crusts on the soil surface and vegetation stress. Radar sensors, on the other hand, provide valuable data on soil moisture content, which is closely related to salinity levels. The relevance of remote sensing to soil salinity lies in its ability to perform large-scale and repeatable monitoring of soil conditions across vast and often inaccessible areas. This capability is invaluable for timely detecting changes in soil salinity, assessing the extent of affected areas, and planning mitigation strategies. In our exploration of how remote sensing aids in the management of soil salinity, it's essential to understand the specific techniques that make this possible. First, let's talk about optical remote sensing. This technique is particularly effective in identifying signs of salinity, such as visible salt crusts on the soil surface and stress in vegetation. It does so through the use of visible and infrared spectral bands, which capture detailed images that highlight these conditions. Moving on to radar remote sensing, this technique is adept at measuring soil moisture content. Since soil salinity often correlates with moisture levels, radar sensors can provide critical data on the distribution and severity of saline conditions. These sensors are especially useful as they can penetrate cloud cover and provide data regardless of weather conditions, a significant advantage over optical sensors. Data is commonly sourced from several satellite missions, including Landsat, which has been in operation for decades, the Sentinel series, which provides high-resolution data, and MODIS, which offers daily global coverage. Together, these satellites provide comprehensive and up-to-date information, essential for mapping and monitoring soil salinity across the globe. As we explore the role of remote sensing in managing soil salinity, let's highlight the distinct advantages that make this technology particularly valuable. One of the primary benefits is its capability for large-scale monitoring. Remote sensing allows us to observe and analyze extensive areas of land, including those that are otherwise inaccessible, ensuring comprehensive coverage and monitoring. Another significant advantage is cost-effectiveness. Traditional ground surveys, while accurate, are labor-intensive and costly, especially over large areas. Remote sensing, in contrast, provides a more economical solution by covering vast areas quickly from satellites or aircraft, reducing the need for extensive physical sampling. Time efficiency is also a critical benefit. Remote sensing technologies enable rapid data collection and processing. This speed allows for quicker responses to changes in soil salinity, enabling timely interventions and management strategies. Such efficiency is crucial in mitigating the adverse effects of salinity on affected landscapes. By leveraging remote sensing, we can monitor, manage, and mitigate soil salinity more effectively, making it an indispensable tool in our environmental management arsenal. While remote sensing offers significant advantages in the monitoring of soil salinity, it's important to also consider the challenges and limitations associated with this technology. First among these is the issue of accuracy. Remote sensing data requires rigorous calibration and validation against ground truth data to ensure reliability. This process can be complex and resource-intensive, posing a significant challenge, especially in remote or large-scale areas. Another limitation is related to resolution. The spatial and temporal resolution provided by remote sensing technologies may not always meet the needs for detailed studies. For instance, some satellite images may not provide the fine detail required to detect early stages of salinity or small-scale variations in soil properties. Furthermore, the complexity in data interpretation presents a substantial challenge. Remote sensing data collects vast amounts of information that can be difficult to analyze. Distinguishing soil salinity from other soil properties, such as moisture content or organic matter, requires advanced analytical techniques and can sometimes lead to misinterpretations. Despite these challenges, remote sensing remains a vital tool in environmental monitoring, though it is crucial for researchers and practitioners to be aware of these limitations and work towards overcoming them. As we conclude our discussion on soil salinity and the pivotal role of remote sensing in monitoring and managing this global challenge, let's recap the key points. Soil salinity remains a significant issue, impacting millions of hectares of land worldwide. It poses serious threats not only to agricultural productivity, but also to environmental health and biodiversity. Remote sensing has emerged as an indispensable tool in our arsenal against soil salinity. With its ability to provide extensive, timely, and cost-effective data, remote sensing supports the effective monitoring, management, and mitigation of salinity impacts across large and inaccessible areas. Looking forward, the continued research into and adoption of advanced remote sensing technologies are crucial. As we enhance our capabilities in data analysis and interpretation, we can improve the accuracy and effectiveness of salinity assessments. This progression will not only help in managing current salinity issues, but also in preventing future occurrences. Subscribe to GIS and Engineering Academy, and thank you for your attention. Let's continue to explore and invest in these technologies, ensuring a sustainable future for our agricultural landscapes and natural ecosystems.